Thank you very much, and thank you for the SEMI organization for inviting me. I'm so pleased to be here. So SEMI is 30 years old, and my first time in Taiwan was 30 years ago, so I'm very glad. My name is MartinGallezot. I'm with CEA-Leti, which is a European RTO, another one. We are here massively, and I'm going to talk today about wide bandgap semiconductors for data center application. The subject of our forum today is unlocking the future of AI. I think it's pretty much unlocked already, so we're going to try to sustain it. In power semiconductor, the use of wide bandgap started a little more than 5 years ago in production, and it was mainly designed for automotive application. So ICE, but also EV, powertrain, onboard charger, and so on. And the goal of my presentation is to show that in power electronic, application matters. So whether you are developing a device that will be used in DC-DC conversion, or in a data center, or in automotive application, in a car, the features are different, and what you expect of the device is different. That being said, a device vendor needs to make a living, so they need to find trade-off to be able to sell their device in as many markets as possible. So I think that's the topic of my talk today. Gallium nitride and silicon carbide usage in data center have been well covered this morning by the likes of Infineon or TI. So I'm going to try to have a little different approach and show what will be the device of, not of today, but of tomorrow. So I think everyone is aware now of the big figure. There is a lot of power waste in data center from cooling, but also from conversion. So I think everybody agrees that reducing this waste should be a first priority goal. There is another goal that I think was not mentioned too much this morning, is the cost of this device, because one of the reasons of this waste is because the conversion cost is still high. So to put it simply, and I could leave it at that, the goal of us power electronic semiconductor engineers should be, one, to reduce the waste, but also to reduce the cost so that there is no more waste. So a breakthrough is needed, definitely. I think all the speakers this morning and this afternoon show this catastrophic figure of what will happen if we continue to power our circuits the same way. And the good news is that the breakthrough is coming. So today's limitations are all along the chain. So both the cooling loss and the loss in the device themselves, so the energy that is lost converting and the energy that is lost converted to heat, all that is what we want to get rid of. So it's a long chain that starts from 10 kV and that ends up at VDD. I'm not going to be able to address all the issue in this chain today. So I'll address mainly the active semiconductor device issue, so the transistor issue, to make it clear. And among the issues that I will not address, but that I would like to mention as a food for thought is, one is the passive devices, and especially the magnetics. To my knowledge, there is not enough R&D involved in this part of power electronics, because magnetics are still responsible for a big part of the loss. And second of all is everything related to the, I would call that the last millimeter of the chain. So everything that happens between the input pin of the server or the GPU that you are powering and the power bus inside. So stuff like hybrid bonding, wafer-to-wafer, full power usage, so, and of course, backside power delivery. So this I will not address today, but I think they are important topics, so maybe it'll be the subject of another presentation. So as was discussed this morning, the first thing you can do once you have decided to use wide bandgap material for your transistor, the first thing you have to do is to rethink the topologies. The old world was made of silicon IGBT, which is a fantastic invention and that took us probably 10 to 20 years to fully exploit as a power system designer. So the topology that was based on the silicon IGBT need to be rethought, and there are many different options. The only thing that is certain is that you should not use the same topology as what you did with silicon. In this slide, I've shown a couple of topology. I think that they are quite similar to what was presented this morning. There are still variation on which is the upper voltage, DC voltage that you start with. Of course, 800 volt is the way to go, but there are still many data centers that rely on 400 volts. So I think we got to consider both. The general idea in this topology is the same. I think it's that you start with SiC for the higher voltage and you finish with gallium nitride for the lower voltage. So that sounds very straightforward, and so one could say there is nothing new, so let's just stop the presentation and go have a drink. I think not. The topologies are this one, but the devices, the wide bandgap devices of the future will be still different from that of today. Today, most people are using, in silicon carbide, are using a plain old MOSFET, and we'll see that there are many other options. And same in gallium nitride. Probably everybody here has talked about PGAN, PGAN gate, which is the default EMOD device, and there are other solutions, and they are not that far away in the future. So again, Leti, CEA-Leti idea is to build a full chain starting from the highest voltage, so 6.5 kV or even 12 kV, down to the lowest voltage, 0.8 V, or 0.7 in some cases. And since we are not manufacturing power supply, but only developing them and transferring them to power supply manufacturer, we have much more freedom to think out of the box because we don't have a box. So we can fit that in any box. So what I will show here is an example of topology that we came up with, but there may be some other option. And what I did is I counted the number of transistors in each topology so that those of you whose business is to sell transistor can figure out a little bit what business there is beyond. So I'll start slowly with the silicon carbide stage. As I said, most, if not all, silicon carbide devices that are on the market today are plain old MOSFET, as pictured in the schematics below. They are still much more efficient than their equivalent SEIGBT, but they have some drawbacks, and especially their on resistance is still not as low as it could be. Still, let's be positive and talk about the benefits. So safety is one. So there is the breakdown voltage of silicon carbide have a very wide margin as compared to the utilization rate. So there is no breakdown risk. The heat dissipation, thanks to the silicon carbide material itself, is naturally good. So there is not much that you have to do about heat dissipation inside the device. You have to take care of heat dissipation outside the device, but that's another story. And the overall reliability is good. So the main factor that needs to be improved in this silicon carbide device is the on resistance, and to some extent the switching speed. I say to some extent because in this higher voltage part of the conversion chain, the switching speed is not that big of a deal. It's a bigger deal when you go down the chain. I'd like to mention one thing that is a very easy step to take to improve your SiC device is to start with a better substrate. Yeah, that sounds a little simplistic, but it's actually the case. And I'd like to introduce a substrate. It's a product of a company called SOI Tech, which is actually a spin-off from CEA-Leti. It's called Smart SiC, and it's actually a low resistivity substrate that has a thermal and mechanical role, on top of which is a layer that has an epi-ready behavior for the SiC layer. So that is engineered, it's an engineered substrate designed to facilitate the epi growth and to provide an excellent channel material. These products have been on the market for some time, so they are available. And the benefit that you get is a better on resistance, and I'll show you in detail, in greater detail, how better it could be. But the long story short is that, and that's what is shown in this curve below, is that it offers at certain voltage, it offers a much better on resistance. And if you look at the different contributor of the resistance in a SiC MOSFET, so starting from the substrate to the channel, to the GFET, the drain contact and the drain region, the breakup of the on resistance in percentage is compared here from a standard monocrystalline silicon carbide substrate to the Smart SiC substrate. So the loss in the reduction in the loss is immediate with that sort of device. So you can keep on building the same device, but using that substrate will provide you immediately several tenths of % of gain in your conversion chain. So that was the easy one. It's available. It's a product that is available. You can buy them starting today, and it provides already a way to reduce that waste that we were talking about. Second step in the silicon carbide roadmap and loss reduction plan is to use more modern devices. So here is the roadmap of silicon carbide devices that we have at Leti. The spirit of this roadmap is simple, is reduce our on through device geometry. And that starts with trench MOSFET, which I'm sure some of you are also studying in your own R&D groups. And that goes up through what we call vertical FinFET, where we expect to cut the channel, the whole channel resistivity by 1.5x by using both this new device architecture and the Smart SiC substrate that I mentioned previously. One thing to notice is that these new devices will require better CD, so better litho than what you may have today. So that's one thing to take into account. We're not talking about, a deep UV type of lithography, of course, but we're talking about better than what is used today. And of course, there are still some research to be done to reach these vertical FinFET type of device. We expect to demonstrate them ready for production by 2030, which is 5 years from now. Okay, on top of this main roadmap, we also have a super junction roadmap, and it may be useful for some other application that are not power conversion in this data center, that are not automotive, but that are new application. Thinking, for example, on solid-state breakers, which is an application that we didn't talk much about today, but that has a potential for a market or even other. And for this one, we plan to reduce the epi resistance by a factor of 3x. Okay, so here is a nice TEM image of what could be a silicon carbide vertical FinFET on the left. Okay, so that's all for for silicon carbide. So let's talk a little bit now about gallium nitride. And I want to introduce a type of device that we've developed at CEA-Leti. It's an isolated gate device. We call it MIS-EMT. So it's a device whose concept is known, I think, to everyone, but to my knowledge, there are not many companies that have tried to do it, and even less that have succeeded in doing so. So what's the advantage of having an isolated gate in a gallium nitride device? Well, there are several. We're going to talk about them. But other than the specific advantage of the isolated gate, this structure uses an epi and the first layer that are very similar to the PGAN one. So there is not much difference in terms of manufacturability. They are manufactured the same way. As was introduced in the LAM presentation this morning, there are specific challenges related to the recess of the gate, and this challenge were tackled, and thanks in particular to LAM. So that's for the device itself. Now the usage of this device in the data center in power conversion, I'll get back to this later. We already support 1200 volts with standard silicon substrate at Leti. So the gallium nitride device that we have already support 1200 volts, and that's very useful for automotive application. In data center application, we think we don't need that, thanks to cascading. We think that we should, rather than trying to support a higher breakdown voltage, we should focus on lowering the cost of the low voltage GaN. We think that this is what is important because by cascading the device, you can very well live with a lower breakdown voltage, but then your device better be very cheap because you're going to need a lot of them. So that's what I call cascading. So that schematics is probably hardly readable. It's an example in the 400 volt scenario. I'll show an example in the 800 volt scenario. In that cascading approach, the 400 volt to 1 volt requires 48 GaN transistor, 16 GaN diodes, and 8 planar transformer. So that's a lot of device. But then the device on the right side of the schematics, there could be 100 volt device. So simpler epi, lower cost, and probably much more lower cost than the silicon carbide device because gallium nitride is on silicon, so it doesn't require an expensive substrate. So same for the 800 volt, this time 96 GaN transistor, 32 GaN diode, and 16 planar transistors. So with that scenario and with existing device that we manufacture at Leti and that I'll show some footprint example later on, you have 2.4 kilowatts, 800 volts to 1 volts complete conversion. So here are some screenshots and footprint of these transistors. So it's they are 150 volt transistor, and some are only 100 volts. The purpose of this wafer is to do development and R&D, so that's why you're seeing lots of different size and shapes. But basically, we're going to open up this as an MPW platform, just like IMEC does. If you're interested, and I'll show you detail in the last slide, you'll be able to use this platform with a PDK from Leti to design your own GaN transistor. And when I say transistor, I should add, well, first it's called an amp, and second, there will be some additional IC capability so that you can merge this transistor and integrate a little bit. So these are examples of board that we have manufactured so far with this cascading solution. It's still a work in progress, so we hope to be able to show a complete demonstration of a working unit by the beginning of next year. But I wanted to introduce that concept to you. Again, it's not the only concept, and when you have good wide bandgap device, there are many other concepts that can work. The advantage of this one is that it is based on low voltage devices, and low voltage devices have an advantage in terms of stability and cost. Let's get back to that isolated gate device. So I mentioned that there were some advantages. I think the main one, it's the ability to drive larger amount of current because the gate has sort of a boost mode. In the PGAN gate, You all know that you got to be very careful with the way you drive it, and if you exceed some voltage, it will break. In the isolated gate, there is much more flexibility in the driving, and also there is a possibility to drive probably 10 to 15% more current as compared to a P-GaN. So that's very useful in application where you need very high current density, like driving a LiDAR, for example, or in some other industrial application where you have most of the case at a certain power level, but some special case where you need this so-called boost mode with a higher level. So in the curve in the lower left, it's an IV plot with a gate voltage ranging from 0 to 10 volt, and you see that in the last step, when you get close to 10 volts, you have this possibility of a higher current as compared to the P-GaN that saturates much quicker. So that's true at ambient temperature. It's a little less true at 150, but it's still true. And since the P-GaN at 150 has also a flatter saturation region, the advantage is still 15% more current. So that's one advantage. The other advantage is because of this gate voltage margin that I mentioned, the likeliness of something going wrong with the gate drive is less. And as a result, the robustness, and especially the robustness when you are driving multiple die at the same time, is more. So we plotted here a gate oxide TDB estimation with a different VGS voltage. And we see that the line goes very nicely to 10 to 12 years of lifetime for that kind of device. Again, these are not devices of the future, these are devices of today. So the device itself is production ready, and it is available as a 650 volt or 1200 volts epi variants. We also have devices of tomorrow in gallium nitride. So first of all, 12-inch gallium nitride. So we are the proud owner of two Hyperion MOCVD reactor from Extron. We have a similar work with SYTech that is similar in engineered substrate for gallium nitride. And we're also working on advanced concept of GaN FinFET with a potential for 10x R-on reduction. So that's what is showcased in the lower right schematics here. So it's a tri-gate device with multiple channel. I think it will be the subject of another presentation, and we'll be glad to present that maybe next year or the year after. This has really a lot of potential. It's still under development, but it's something that should be in the 2030 time range that should be ready for production. Okay, so I'll finish with this multi-wafer project for the isolated gate GaN. So the PDK release is next year. The first tape out Christmas 2026, and the next one February 2028. So it's still far away from today, but you guys that design chip, I'm sure you like to have some time. So if you're interested to participate in the MPW, please let me know. We'll be glad to have you on board. Thank you very much.